Welcome to our webinar today. My name is Ian Trevoranis. I am the Product Line Manager in the Americas for HORIBA's Particle Products. I'll be hosting the webinar. With us also is Mark Buemiller. Mark is a Vice President of HORIBA with the Particle Division. And Mark's going to be speaking to us today about sampling, which is one of, if not the most important factor to getting reproducible particle size results.
An often overlooked, very important topic that we would like to cover tonight.
There you go.
But first, usually I start with a joke, but today I was thinking I was going to start with a quote. So we were talking about Ohio and astronauts, and so the question I asked Ian is, what were the first words uttered by Neil Armstrong when he set foot on the moon? And what most people think is one giant step for man, one giant leap for mankind. Actually, before they cut to TV, the first thing he said is, as he put his feet out there, is, "It's powder." So that was the first statement uttered by a man on the moon. I actually heard that from Reg Davies, who headed the Parsec group at DuPont for a long time. He was one of the person who I was considered one of my mentors in this business. And dealing with powders is just a tricky business. And a lot of what we're going to talk about tonight is dealing with powders, how we're going to do the sampling, how this is the first important step in generating good particle size distribution information. And, you know, I don't think it's a huge topic. I think it's probably just going to be like a 35-minute discussion or so. But what I'm going to do first is show a workflow. This actually comes from, if you haven't seen it before, NIST published a very nice book on recommended practice guide for particle characterization back in 2001. Ajit Jilla kind of stepped in and did a really nice job putting this book together and then moved on to do different things within NIST. But you can download the whole book from the NIST website, and there's actually some detail in there on sampling, more thorough than what you'll see tonight even. And it's free, so this is probably the first nice tidbit I'm giving you is a nice little reference. You could go to the NIST website and find this recommended practices where they talk about all of the steps to generate good particle size distribution information. We're going to start up here today. We're just going to talk about the first two steps. First, we have to get a sample out of the bulk, and then that sample comes to the laboratory, and we're going to do some subsampling on that material and get it into the instrument. So what we're discussing tonight is just the first two steps, but there's a lot more to generating good data, of course. If we bring that sample into the lab, we probably have to disperse it, either measure it in a dry powder feeder or disperse it in liquid. And I'm thinking dispersing powders in liquid might be the next topic I should put together for a webinar and some other information. There's whole fields of study in terms of sample preparation. We do have a webinar on sample preparation for laser diffraction already on the website. We have to make sure the instrument's working properly. I would use verification rather than calibration here, and we have information on the website and webinars on system verification. Make the test. We have lots of information on how to use our instruments for that. The data processing, I guess we talked about the theory in various places on our website. And also, you know, data interpretation, what do these numbers mean? And then we report the results. But today we're just focused up here in the sampling area. But there's more to it than just the two steps you see right there. So let's just think again, if we look a little more closely here. So let's start thinking about this as a strategy. How are we going to go about doing good sampling of powder and get it into the laboratory for the measurement? Well, we have to decide how much volume should we take. And that is a field where actually there's a theoretical approach that can be applied to do that. We have to know something about the powder characteristics. If I'm dealing with a very free-flowing material, I'm going to probably deal with it differently than if it's a very tacky or material that tends to stick together. How much powder do I need to get to the instrument? What sampling techniques or tools am I going to use? And then go out and get those samples. And that's kind of where I'm going to start focusing this discussion. I'm not going to go up to, you know, if you make 10 tons of cement, how much do you have to sample to bring it to your instrument? That's usually something that's figured out either by the people running the plant, or it's been assigned to somebody to make those determinations. When it comes into the lab, then we do things like divide it. But what's very important is once we get into the lab, what we should be doing always is before we just start making measurements is let's have a strategy and let's make sure that the strategy we've used is appropriate. So as we take samples into the lab and subdivide it, we should be doing some kind of homogeneity or reproducibility test to make sure, is this strategy working? So this is usually where the lab operators need to start getting involved, is making sure that what we're doing is working, and the way we're going to define that is the method reproducible? So if all of this is working, then we'd go about doing the other optimization of the measurement steps. But we have to make sure we do this, and this is kind of where I'll be focusing some of the discussion tonight. If you look at the errors involved with particle size analysis, this is error percent on my y-axis, and this is particle size. And as you get to really small particles, usually sample preparation is the issue. So if you're dealing with an aggregated metal oxide that's 20 nanometers, that powder isn't going to be terribly stratified, or it's not going to be very difficult to get a representative sample. The trick is going to be to disperse those aggregates into individual particles. So for small particles, it's all about sample preparation. And I picked up my wrong drawing tool. Bear with me a minute while I try to get this back to where I want it. So I chose a pen color earlier. I always use HORIBA blue. Sorry for the delay there. But then I lost my tool, so I'll just keep talking while I grab my arrow again. So small particles, that's over here where sample preparation is very important. What we're going to talk about tonight is over here on this side of the curve where we're talking about sample extraction. We always like to say, well, the instrument error, that's really small, don't worry about that. Certainly that is an issue, and we design instruments to minimize that error. And as we have other training material on the website about minimizing that error, important, but not tonight's discussion. It's really about sample extraction. And the larger powders are really where this becomes an issue. So how do we define a larger powder? And I don't know, maybe that's at 50 microns, maybe it's 100 microns, somewhere around there. When you're dealing with powders up in this size range, how we do that sample extraction is probably the most important step in generating good reproducible results. So that's the kind of samples. If you're working with these kinds of samples, then this is a very important issue, and we need to take care of how we approach this. As I talked about accuracy, then I realized I threw in this slide, well, what do we mean by accuracy? So just a quick run through what might it be, and there's several influences into the accuracy or the errors. I really should just be talking about errors. What errors come into the measurement? And we can look at errors in terms of accuracy. Accuracy means I'm getting an answer of 100 microns. Was that really 100 microns, or was it 110? And there what you're really trying to say is the result I generate, how does that compare to a referee technique? And the referee technique in our business is usually the microscope or some kind of direct measurement like that. So accuracy is really about, does the result I finally generate make sense compared to a referee technique? The place where it might where the operator of the laser diffraction analyzer might influence accuracy are some choices like refractive index selection for smaller particles. If you choose an inappropriate refractive index, you'll get an inaccurate result. If you don't disperse the sample well, that will affect your accuracy. It won't match referee techniques, and just your method development. What kind of method do you use working with the instrument? So these are the kinds of influences an operator of an instrument would have on the accuracy. We can also talk about repeatability. Usually in our business, when we talk about repeatability, we're talking about a sample that's suspended in the instrument. Usually it's a suspension, and we're recirculating it. And we're seeing, do we get the same result as we recirculate the sample? And it's a good way to test, is the sample stable during the measurement? If it's not stable, we're doing something wrong. We should correct for that kind of problem. Reproducibility errors mean we take our sample, we do whatever we have to do to disperse it, we do the measurement, we clean up the system, and we repeat that process. This is reproducibility, and this is where sampling starts playing a role, because if we're not sampling appropriately, then we're actually putting a different sample into the instrument each time. So if we have poor reproducibility, then sampling is somewhere we should be investigating as we look at the overall picture of taking these measurements. So if you're having problems with errors because of reproducibility and you're dealing with larger powders, this is probably really where what we're going to talk about today might help you generate results with less error. So a few slides about sampling powder from bulk. So people who use these instruments who are dealing with powders, usually, you know, there's a plant. We spend all of our life in the lab usually, but out there's a plant, and out in that plant we're making a product, and if that product is a powder, the powder is being moved from point A to B somehow. Maybe it's on a belt conveyor, maybe it's going through some kind of pneumatic line. And somewhere along the way, we have to take some portion of that powder and remove it and bring it to the laboratory. And this is the bulk sampling. And there's various ways to do that we'll talk about. The general idea is we want to take that sample as the powder is moving. And then we want to find a way to take that sample so that what we take out is representative of the whole. And in bulk sampling, that's the important step. Let's make sure it's representative what comes to the laboratory. And if we're dealing with high throughput powders, probably it's flowing through some kind of a gravity feed at some point. And we have various samplers we could attach to the process line, such as an auger sampler, where maybe there's a screw here that takes a small amount and then it's collected in the sample bottle, which is then sent to the laboratory for measurement. Or there's other ways to reach in and take that sample. This is, for instance, a cross-cut sampler where this sweeps back and forth across the powder flow. And then this sample flows down here again into a sample jar, which is sent off to the laboratory. And there actually are ways, if you know, for instance, the speed, the flow of the powder, and if we know the mass flow of the powder, then we could actually come up with how big should the cross-cut sampler be. And if we know the speed that it moves at, then we can actually calculate how should we scale this to the process we're working with, and then how should we design this, and how often should we take measurements and bring it to the lab. If you do want more information on this part, how we could design this so that it makes sense, so that what we're removing is representative, there's actually a very good powder technology book by Masuda out of Japan, and this is a reference I'll give you as well. If this is the portion of tonight's talk you find more interesting, this is where I would direct you to get some more information. There's other books too. Terry Allen's book, I'll have a reference in here later on, covers the topic, and the most recent one was actually by Hank Marcus. And that was just published 2 years ago. I'm not sure if I have a reference for that in here. If somebody needs that reference, they can send me an email. I'll be glad to supply that.
Hey, Mark.
Yeah.
We have a question from Damon asking, in general, how repeatable is the LA950 while recirculating? Is it 5%, 1%?
Well, for the ideal easy sample, it's like 0.1%. If you take 1 micron polystyrene latex, which is the easiest sample, and recirculate it, isn't that the data we show, like 0.1%, Ian?
0.1% for polystyrene latex.
Yep, so that's the instrument error, but that's the easiest and best behaved sample. And anyone can generate good data using polystyrene latex. For real-world samples, that number can vary quite a bit. Your sample has to be stable for that number to be low. If your sample is dissolving or aggregating while you're recirculating it, then that repeatability is going to get worse and worse. So some part of that is dependent on the sample, but the instrument error, which I showed several slides ago as being very low, inherently it's a very repeatable technique. But if you're measuring, let's say, a powder coating that you're dispersing in a surfactant and measuring it, checking repeatability in your LA950, it better be below 2 or 3%, or you're doing something wrong with the numbers I'd throw out. How would you feel about that, Ian?
Yeah, I would think that if we were doing method development for the LA950, and we'll be specific about the 950, then 5%, Mark is entirely correct, it depends on the sample. Most applications I would definitely expect to have a D50 median value with lower than 5% repeatability. If it's 5% or higher, then I would definitely think that either the circulation pump isn't spinning fast enough, or there's just some issues with the material. And this is
along the way.
Yeah, and the density of the particles is going to have a large part to play with it too. We have a user who's measuring depleted uranium, and that is super dense, and so they can't circulate that material for more than a few seconds before it completely settles out. So there are ways to improve your repeatability as well. You just need to know how the sample is interacting with the system and vice versa. So that's a general answer, which is what you'd asked for. But specific applications require specific method development. And this has generated a few follow-up questions too. Pragnya is asking, how much could the dense particles have a chance to settle down doing the repeatability? Yeah, so she's hitting the nail right on the head. If you have a multimodal mixture or a material, a sample rather, with multiple materials in it, if one component is much more dense than another component, the denser material is more likely to settle out over time, which could look like the material is dissolving, or it could look like the material is just disappearing, when in fact it could be that the 950 is not spinning fast enough, or maybe you need to wet the powder a little bit more. These are all issues that should be addressed through method development. You know, there's 1,000 applications with the LA950, and so potentially 1,000 different answers. So that would be the best approach, specific method development.
Okay, onward.
I think so. There are some more follow-up questions, but we'll address those in the Q&A at the end.
Okay, very good. Thanks for those questions. Let's say that the sample you're going to measure in the lab actually has been transported to your site in a drum. Just a few slides now of how should we remove the powder from that drum. Well, what you shouldn't do is just take the top off and scoop the powder off the top. The better approaches are to use sampling systems. These images are courtesy of Sampling Systems from their website. So here we see someone reaching into a drum using, there's kind of two approaches. There's a powder thief, where you put this device down into the system. Then you kind of pull back on the outer casing, the powder falls down into here, and then you push that casing back forward and remove the sample up out of the drum. So powder thieves are one approach, and you can choose different sizes of this, depending on the size of the drum, how much sample do we need to remove, etc. So we have the approach of the powder thief, and we also have a slot sampler, where you put this device into the drum and then turn a handle up at top, and then these openings become open, the powder flows inside. Turn them again, it closes up, and then these pockets collect the sample and brings the sample out, which can then be put into some container to bring the sample to the lab. This has the advantage of you're actually sampling at different heights within the drum, because as we talk later on about powder segregation, the particle size distribution down here may be very different than up here. And today's goal is to make these results in the lab very meaningful, and it's only meaningful if what we generate in the lab is representative of the whole. So this is probably the most rigorous approach, where we're actually taking powder from different heights in the drum, and this would take into account concerns with segregation. So that actually probably is the most rigorous approach if we're taking samples from drums to do the measurements into the laboratory. So now we either have used an industrial sampler to remove powder from the flowing stream, or we've used some appropriate slot sampler or thief sampler to take sample out of a drum, and that's going to come into the lab. Let's just talk about the scale of where we've gone from. So you know, who knows, I mean the cement plant, and I don't know why I keep picking this up, so let me see if I can just make this go away again. There it is. You know what I need, Ian, is just to actually use a mouse when I do these rather than my little pen here, which I'm using here. So I go to here, then I pick this tool up. Bear with me a minute. So this is my toolbox. I pull it over here. So what we're doing in the plant could be generating tons of material, and then I can't switch this over to file because I lose that. So I have to hit escape again, go to here. I apologize for the delay here. So Ian, you're watching what I'm doing. I'm not sure what I'm doing wrong today, so I'm going to switch over to using this little pointer instead. Or is that too slow? Does that not update quick enough, Ian?
No, it's working okay.
Yeah, okay. So we might generate tons of material, and a kilogram might be removed from the process. And then that's brought into laboratory, but what's brought into laboratory, not even all of that is analyzed, and now we're going to talk about this subdivision of the powder that comes into the laboratory and how much of that is going to be used for the measurement. And how much is used for the measurement depends on how we're doing the measurement. For instance, if we're using a dry powder feeder, then if we're working with a dense sample, we might be measuring up to, like, we could put 50 grams of a dense powder on a dry powder feeder tray, and then ideally we'd measure all 50 grams. But if we're taking a low-density powder and we're going to disperse in liquid, we might use only like 0.05 grams. So we may be measuring grams or milligrams depending on the kind of measurement, the material properties, and the method we're using. So there could be a big difference in the subsampling in terms of how much of this are we going to use for the measurement. And I'm still going to try to grab my arrow again. I prefer that. There we go. So what we're going to talk about now is getting that powder from the container that came to the lab into the instrument. The worst thing you could do is what I show down here is you just reach in and use a spoon or spatula and take powder off the top. The concern here is segregation. Segregation can occur various ways. The most common way is like percolation segregation, as you see here. And what's going to happen is if this powder has a broad distribution and is free-flowing, as you agitate it or experiences vibration, which would happen, for instance, if it's being transported in a train car, what's going to happen is the smaller particles can actually find their way down towards the bottom of the pile, and essentially the larger ones percolate up. So the concern with just scooping off the top of a powder jar is that you'll be biasing your distribution towards the larger particle size. And what we're trying to do is get a reproducible result. So you can get away with this for a narrow distribution, and you can get away with a lot of things for easy samples, but when we're dealing with a broad distribution of large powders, this is the first big important message of today's don't do this. Don't just be scooping that off the top. That's the kind of practice that will get you into trouble. So what should we be doing? Well, at a minimum, what we should do is, first of all, this sample ball that comes to the lab, let's hope it's not completely full. That's a no-no. We should never have this bottle more than 2/3 full. One of the reasons being what we want to do is at least tumble and mix this bottle before we start taking sample out of it for the measurement. And if it's filled to the top, then we can't do any of these mixing steps. So we could roll it, we could tumble it, get this appropriately mixed, and then if we somehow kind of reach into the middle and use a spatula and remove that portion and put in the instrument, you know, then all of a sudden at least we're doing okay in terms of good practices doing sampling with powders. So this is at least the next step you should go to. Progressively, we're going to be suggesting more rigorous approaches which will reduce your errors, but at least be doing this. What some people do could be other approaches to sampling. Now, we'll talk briefly about coning and quartering, which you only do with large free-flowing materials, where if you pour it onto your table in your lab, you actually would create a cone. For a completely free-flowing powder, you wouldn't get a cone, you would just spread out. But usually what people do is they'll somehow kind of cut the top off the top, and then reach in with a device, and you can buy cone and quartering devices or use a sharp edge tool and start cutting this into 4 different portions. And if you're lucky, you take that portion and measure it if it's the perfect amount for your instrument, but otherwise you might take this amount and then cone and quarter it again. So this is not a terribly rigorous approach, but still being used, and if people do it properly, this is much better than not doing anything at all. So cone and quartering is still an approach used for large free-flowing powders. The next step in terms of a rigorous approach, and more where we say this is where we start with recommending these kind of practices, is just go and get a chute riffler. And so what these do is you pour the sample up here, and then as the powder passes through this mechanical device, there's no moving parts here, it just falls down, and there are blades here, and these blades just separate out the powder into 4 or more bins, as you see down here. And this bin may then be just the perfect amount to put into your instrument, or you take the amount in that bin and run it through the riffler again, the chute riffler again, to reduce the amount until you have the amount you need for the measurement. Chute rifflers are easy to use. They don't cost much money. And if sampling is going to be important for your powders, this is, I would nudge you at least in this direction. So at least have a chute riffler. If you're dealing with a wide distribution powder, this makes a lot of sense. If you're working to generate the best possible results, then we start talking about using a spinning riffler. And this is the best method for taking a powder sample and cutting it down to the portion you need for the measurement. I have kind of a cartoon up here, then an image down here of the unit we actually have in the lab there in Irvine, California. What happens here is the powder is on this tray and it vibrates. And as it falls off the tray, this is spinning around down here, and the sample falls into either test tubes, or into little metallic collectors. Then you take one of these or more of these and bring it to the instrument for the measurement. So this is the best practice approach and what we recommend when you're doing important work. And actually the Irvine lab has pretty good notoriety, and there's been various ASTM tests, etc., where bags of powder show up in Irvine, and they have the skill set and know how to use this, and they do the riffling and then send it back to go out to interlaboratory studies. So there's a lot of skill for using these out of the Irvine lab. I'm not sure if microscale is still in business. They're available from Quantachrome, from Retch, and this is what you should be doing. This is best practice if we're needing to do subsampling of powders in our laboratory.
Unfortunately, unfortunately, microscale is not in business anymore.
Yeah, that's what I thought I heard. That's too bad, because that was always my favorite, and that's the one they in the lab there in Irvine. There are larger scale rifflers here. I think this probably just comes from Retch page or something like that. So you can go to retch.com. They have rifflers, not on as small of a scale as the microscale was, but for sample splitters, Retch is a really good place to go to look for sample splitters for doing that level of good practice. If we're going to use sample splitters, there's actually a little bit of science behind this too. If we know the particle size of what we're dealing with, note this is in millimeters. We're talking about large powders here. The smaller the particle size, the smaller you want these opening widths. So in general, we tend to buy the smaller of these devices. Just because most of the measurements we make on the LA950 are down, we can measure up to 3 millimeters. So you see that already puts us down here into the smaller of the sizes for these sample splitters. Down here, this is just kind of strategies for doing the sample splitting. And this comes from, there's actually an ISO document on sampling. And what it suggests is if splitting this once doesn't get you down to the volume or the weight you need, there's two ways to do this, right? So you split it in two, and then you take that portion and you split it again, or you split it into two, combine these, and split that again until you get it down to the actual amount you need for the measurement. Either of these is appropriate, but just kind of the two strategy used for using sample splitting to get it down to the volume we need for the measurement inside the instrument. A few comments on practical terms. One is cleanliness. And if you're using a splitter or a riffler, you do need to clean it after each use, and I sometimes wonder if that's why we aren't using these more often. Who likes to clean, right? But find an easy way to clean it. The bigger the powder you're working with, the less rigorous you need to be for cleaning. You do have to avoid cross-contamination. It's not really so hard. Another step to consider is when you're doing these steps, don't be in a big hurry. For instance, if you're using a spinning riffler, you want to slow down that rotation rate, because if you look in the ISO document, it actually says it wants like 20 rotations, 20 to 40 rotations before you've completely subdivided the sample. So don't be in a big hurry, because as you vibrate the powder on the vibrating tray there, it's going to start segregating on the tray. And you might have a big jump of the biggest particles at first, and that's what we're trying to avoid. So don't be in a hurry when you're doing these subdivision steps, especially when you're using a spinning riffler. And of course, be careful. If you're dealing with a dust or powder you shouldn't be exposed to, do this in a way that you're not exposing the operator. So it's a few practical concerns when we're going through these powder subdivision steps. So let's talk now about the errors that come from different approaches to sampling. And this is the data that everyone shows. Terry Allen put this book out a long time ago, not 1934. I think there's a little issue there. So this is actually data which was a bimodal distribution. And they said if we do scoop sampling and spinning and table sampling, shoot riffler, cone and quartering, for a very difficult sample, what kind of standard deviation do we see? If we do 3 measurements and we look at the standard deviation of the measurements, what you would see from this historic study, cone and quartering gives us the worst standard deviation. Scoop sampling for this operator was a little better. Shoot riffling became acceptable. Spinning riffler, the standard deviation falls down into the noise, and that's where you want to be. So that's the moral of this story. Spinning riffler is best practice. Shoot riffler is very good practice. Other than that, you're probably not generating the most reproducible results you could. So I think a month ago I said, you know what, we haven't written a white paper on sampling yet, so I did that last month, and I wrote, I don't know, 20-page white paper on sampling. And I said, well, I can't just show historic data, I'd better generate my own data. And so what we did is I went out into the lab. I spent the summer in Irvine, was working out of the Irvine lab, and I found a large sample for the LE950. Not really large, this is a mean particle size of 40 microns. So this is a little on the small side of where we say sampling becomes very important. But it was just a realistic sample I found. And what I did is I took a powder and I just brought it over to the instrument, dispersed it in liquid, and did measurements. I did 3 measurements. And the way we like to describe reproducibility is using the coefficient of variation calculation. So I look at my D10, D50, D90, do at least 3 measurements. You look at the mean, the standard deviation, coefficient of standard deviation. The coefficient of variation is standard deviation divided by the mean, mean divided by standard deviation divided by 100. Multiplied by 100 to get it to a percent, sorry. So down here you see we're at 3% using a fairly sloppy technique. But then I took that powder over to the spinning riffler and then took a portion from the spinning riffler and used that for the measurements, and my reproducibility improved tremendously. So I got it down to where it was like 1%, and that's really where we want to be. So someone asked earlier on, you know, what should I expect for repeatability? This is the harder test. This is reproducibility. This is do the sampling, disperse it, measure it, clean up your instrument, repeat. And this is really how you should be designing your methods, is to test reproducibility. Then you can have much higher confidence in your results. And these are the kind of numbers you should be generating when you're working with powders, even larger powders. And if you're not getting these kind of numbers, sampling is certainly one of the places you should be looking. So this was for a powder where I then took the powder and I just dumped it into the instrument to measure as a suspension. The next step is I took that, and what I did is I took the powder, and sometimes you want to pre-disperse the powder in a liquid before doing the measurement. So if I take that powder and disperse it into a beaker, and I just take a pipette and remove it and place that in the instrument, I could easily be biasing the result if I'm not catching the larger, heavier powders on the bottom. So the practice we recommend here is you should be mixing this beaker. I tend to probably use a magnetic stirrer. It's sitting on a plate rather than a stirrer that comes from above, but that's just so you get the idea of what we're doing. So if we're dealing with big, heavy powders, but we do want to be doing the step of pre-dispersion, for instance, if we're working with soils, you almost always do this, and you pre-disperse the soil in a sodium hexametaphosphate solution. Some people burn off the organics with high temperature before the measurement. So this is a step a lot of people do, and you need to be mixing this or you're just not going to catch the larger particles. And I wanted to quantify that with a simple study, and what I did is I took this larger powder. This was actually even a larger powder in terms of the D50, not quite as broad of a distribution, but what I did is I just put the powder in a liquid, and these results are without mixing. So I took a pipette and I just took samples from that beaker and put it into the instrument, and I generated coefficient of variations up at 10 to 20%. Completely unacceptable. What I did then is I mixed the sample. You know, I just had the beaker sitting on a stir plate. I had a magnetic stir bar in the beaker. I cranked that up. Then I took a pipette and took samples and put that into the instrument, and my coefficient of variation is down at 1%, 2% again. And that's where we like to be. The other thing you'll notice is the D90 here. Notice how when I was not mixing the system, I actually generated a result where the D90 was highly in error. You know, the D90 is up at 150 something microns, and if I'm not mixing this properly, I could pull out that sample and report this in as being undersized. So this is a very inaccurate result. So a couple of points here. Sampling is important. Also, you have to do reproducibility studies if you want to have confidence in your results. I should have a slide in here just showing you the expectations pointed out in ISO 13320. I should have it memorized, of course, you know, but there's a split between is it above or below 10 microns, and these numbers should be like 5%, 2%. And that's what you're seeing here. So best practices, you have to mix this when you're working with larger, heavier samples, or you're just going to generate results that are in error. And these are the results I generated just this past summer and is in this white paper that we put out. This is what we've been talking about today. This is just going back to the NIST document and talking about we have to test this reproducibility. And this is something we need to be doing. You might not need to do it every day, but certainly if you're working with a new material, and if you're the person in charge of generating reproducible results, these are the steps you have to be doing. You have to be looking at your subsampling. You have to be testing reproducibility, and you have to have goals for reproducibility. Use the ISO standard if you want. 1, 2, 3% is acceptable. 15, 20% is not. We're defining these using the coefficient of variation. I do have some more detail in the topics we've covered today in the white paper that we just posted on the website last month. If you're here at our webinar, you've probably been on our website, horiba.com/particle, where you could find the white paper. To do that, you have to go into the download section. So to get into the white paper on sampling or the white paper on using the method expert for method development or working with powder samples or any of our application notes, you need to go into the website, sign in once here, get registered, and then you have access to the download center where we have all these other documents, including these webinars, which are recorded, and there's a lot of very useful information. I'm glad everyone took out time today to listen to a live webinar, but we do record these and can be viewed at any time, and there's a lot there for training about all these other steps of dispersion, method development, refractive index choice, all these other important decisions that you make in order to generate good reproducible results. So that's where we end today's discussion. I'll slow down now and say, Ian, any questions come up along the way?
Thanks very much, Mark. We do have a few questions. If there are any more out there, feel free to send them in. So a very good question, I think, comes from Melanie, and she's asking if she uses a sample with a complex composition, meaning more than one element, would it change the results if the opacity or the refractive index is not the same between the different compounds?
You can only enter one number for the refractive index value, and what most people do is just a weighted average of the mixture. There is an application note on the website specific to powder mixtures and choice of refractive index. I just kind of cut down to the bottom line very quickly there. There are different ways to do that averaging. There are different ways to test how's it working out, but that's the 10-second answer. Is you can only put in one value, and most people use a weighted average. But if you want the details to that discussion, get into the download center, and I don't remember the number, but it's a refractive index of powder mixtures, I think. And I think there's some detail there on the website on that topic.
Yeah, it's in the training section of the webinars area. I can send you the link after the webinar, Melanie. Okay. We have a question from Bill. Bill's saying that his powders are mostly under 100 microns, but there are some larger particles, greater than 200 microns to maybe 500 microns. The larger particles only constitute maybe 0.1% of the total, but they're very problematic in their application. They typically don't see the larger particles, and that has, I think, something to do, he says, when he sieves the particles, they are obvious on the screen, but the concentration is so low that he would have to sieve many kilograms to get enough to test in the instrument. And he's asking for advice. Is there any better way to measure those particles?
So you know they're there because you're finding them on the screens, but if it doesn't get into the instrument, you were never going to get it measured in the laser diffraction analyzer. How do you statistically say we know they're there even if we're not catching it with the measurements? So that is a little tricky, actually. Let me just ponder that a moment.
While Mark is pondering, I would say, Bill, the easiest thing you can do on the instrument side is simply extend the measurement time. So by default, for a wet measurement, the LA950 takes 5,000 data acquisitions. And that happens in about a second. I would recommend bumping that to maybe 50,000. and see if that captures, if the result from those 50,000 snaps comes with the large particles you're looking for. Because essentially what you're doing is you're giving those few large particles more time to circulate through the measurement zone. And that generally produces better results. If it doesn't, then I would think it comes down to one of two things. It's either that there aren't enough particles in the instrument to generate enough scattered light to activate those detectors, those specific detectors, or it's that the particles are dense enough or large enough where maybe they're settling out, in which case you may need to turn up the pumping speed, or you may need to adjust the density contrast. If you have very dense particles and you're dispersing them in a lower density liquid like water or maybe isopropyl alcohol, you might choose something that's higher density or higher viscosity to help support the particles.
Well, yeah, those are all great ideas, and that's what you would do, assuming it gets into the instrument. I still haven't figured out what would you do if, you know, we have a sieve, but we figured we'd have to put, 10 kilos through to grab the 10 large particles, because that would probably never get into the instrument. So, if it doesn't get into the instrument, I'm having trouble giving good advice of how to report it in the result. What Ian did is give you all the right things to do, assuming it gets into there, and you know, crank up your pump speed, measure it for a longer time. That's how we try to make sure that we're looking at the particles in the instrument. We actually have a larger volume LA950 as well, with 10 times the sample volume of the standard LA950, and some people choose that as an instrument based on knowing there's a few large particles, and therefore we want to put more sample into the instrument. So for people selecting a new instrument, that's the other step we can mention, is we go for, we call it the L2 version, which instead of like 100 ml has a liter of fluid in there. And that just increases the amount of sample, and therefore we have a better chance statistically of finding those larger particles.
Can you hear me, Mark? Mark?
And the L2 is fairly popular with people who do soil.
Mark? Hello?
I'm just going to open my control panel and look for a chat comment here.
Oh, wait, no. I look like my audio's back now. Can you hear me?
Okay, all right.
Yeah, the software told me that my connection had been lost, so. Yeah, you know, the other thing you might, thank you. The other thing you might try, Bill, and this is the last thing I'll say on the topic right now, because we have a few other questions to get to. The other thing you might try is, depending on how critical these large particles are to your application, if just having any large particles is problematic, then I would definitely sieve kilograms of material just to see if they're there. That would be faster than putting it in the 950. If the relative amount of large particles is the critical factor, then yes, that's a little bit more challenging.
Well, I haven't sent an email to Hank Marcus in a while. This gives me a reason to give him an email. I'll see if I can get some idea from some other people on this.
From one of the wise men in particle sampling.
Mm-hmm.
Okay, let's see. The relative amount is the problem, Bill says. Yeah, so we'll see if we can get you some other answers. Let's see. Tom is saying that his particles are at least 2 times larger than what Bill's talking about, but they like the large ones. Well, that's good. Large particles are a problem for so many people. Melanie's asking if there's a difference between measuring dry sample directly or putting the dry sample in water and then measuring it, or putting the sample directly in the funnel which is filled up with water. So Melanie's question is, should she measure dry? A dry powder in the dry form using an accessory for the 950 called the powder jet, should she predisperse it maybe in a beaker and then add that to the wet liquid sampling system, or add it directly to the liquid sampling system as a powder?
Go for it, Ian.
Well, it depends on...
Give us your insight.
Yeah. All right, hold on to your horses, everyone. Here comes my insight. It depends on what your goals are. If typically people choose to measure dry materials dry because they're choosing to avoid a problem of dispersing it in a liquid. So a lot of times people will measure dry because they can't choose a dispersant because of solubility problems, or because it's simply easier to measure dry. If you are measuring something that has fairly dense, then you want to kind of short-circuit the problem of dispersing it and having it settling out of the liquid, and measuring it dry short-circuits it. Because it's a vertically designed powder system, you don't have to worry about powder settling down anywhere along the sample path. If you do want to measure it wet, and you know, the easiest way to see if you get if one is maybe better than the other, if they're equivalent, if you don't have solubility concerns, if you don't have density concerns, a lot of times people just choose what's easiest. And for many people, the dry measurement is easier because it requires less cleanup. You don't have to worry about having a water source on hand. You don't have to worry about spills in the instrument if you forget to hook up one of the hoses one time. It's a much cleaner measurement. You only have to worry about cleaning off the sample chute and occasionally changing out the vacuum bag. That said, if you do choose to measure wet, typically we like pre-dispersing sample as opposed to adding it directly into the instrument. Although there are certain samples that are so easy to run that a lot of times you can just add it directly into the instrument in the powdered form, and it will disperse quickly and easily, and you can save yourself the extra glassware work. The easiest way to determine which of these is going to be better is just to do a measurement of each. Do a measurement set where you add it directly to the analyzer, do a measurement set where you predisperse it, do a measurement set where you run it through the powder jet, and see how the data compares. If one of them is clearly superior to the others, do that one.
Yeah, so try measuring it wet, try measuring it dry. And if you measure it wet, try using a surfactant to wet it. Try using ultrasound to break up agglomerates. The reason some people have to disperse the powder in the liquid is because they're trying to disperse it to the single particle state. And as soon as you put it into liquid, you reduce the surface tension and you start breaking up aggregates. Or you can add energy using ultrasound to break them up. So you also have to do that of just put it in the powder jet and measure different air pressures, put it in liquid, disperse it, use ultrasound, and you have to convince yourself, it depends on your goal. If you want to measure the powder in its natural state, like if it's a powder coating and you want to know if it's going to plug up the pores of a powder coater, you just want to measure it as a powder at kind of the pressure you use it at. But if the goal is to disperse it to the single particle state, then you do your best measurement dry, your best measurement wet, and if the results are the exact same, we usually default for the dry because it's quicker and you don't have glassware to clean. But make sure first, you have to know what it is you want to get out of the measurement, and let the best measurement win is usually how you decide which way you're going to go.
Okay, we have a question from Pragnya. She's saying that 0.05 grams in liquid for low dense powders on one slide. How low should be the density? So I don't recall that slide, Mark. Did you show some? Okay.
Yeah, and I remember when I wrote the white paper, I actually went to the lab and measured the amount of putting into the instruments. So I remember this. It's going to be it's back near the beginning. And did I measure the density of the powder I was using? No. But remember, Ian, you wrote the document too on the amount of sample used when you used magnesium stearate and some other samples going into the mini flow. Mm-hmm. And didn't you get it down to, what was the smallest, like 20 milligrams or something?
Oh,
remember the smallest volume?
Smaller than that, but let me check real quick.
Yeah, so Silica is like 2.2 density. Some of the powders you looked at, magnesium stearate, probably like 1 point. It's probably just under 2 grams per cc is probably what we're looking at for the density of the powder I was working on. And yeah, you even can get smaller sample sizes of powder into liquid. It depends on which sampler you're using. I was using just the standard built-in recirculating unit in the LA950. There's something called the mini flow, which gets down to the liquid volume, I think is what, around 20, 25 ml, Ian?
30.
30. And Ian did a study of how small of a sample we're going to measure. It turns out the scattering from the sample mattered too, as I recall, because you looked at a silica and then you looked at pharmaceutical excipient, I seem to remember.
Yeah, I looked at 3 samples, one of which was a 30 nanometer colloidal silica, and that required 132 milligrams compared to a 10 micron magnesium stearate that required 165 micrograms. So several orders of magnitude difference, and that's just because larger particles scatter more intensely than smaller particles. So very low, to more directly answer your question, Pragna, how much sample is required depends on basically 3 factors. 2 of which you know, and 1 of which is very difficult to know. The 2 you might be able to know would be what the size of the particle is. So if you have very tiny particles, even 50 milligrams of material are going to have so many particles in there by number that you'll be able to generate a pretty decent amount of scattered light, which is positive. The other thing you might know would be the density of the particle. So if you have 50 milligrams of a low density material, that will mean more particles. If you have 50 milligrams of a very high density material, then that might be a particle, which is not positive. And then the one contributing factor you probably wouldn't know would be the scattering cross section. Yeah, so essentially how efficient is the body of scattering light. So in that case, you're looking at a titanium dioxide particle that's going to be scattering much, much, much more light than a similarly sized protein, let's say. So, I hate to give you a wishy-washy answer, but that's all we have.
It depends. That's always the answer.
Yeah. For 50 milligrams of material, that's easier when you have a lot of material. So that favors low density and high scattering cross-section materials. If you're talking about manganese dioxide, then 50 milligrams probably won't go very far because that's a much higher density material. Let's see. Melanie asks a question. Working with a sample from a mine, only 0.1 grams or less is sufficient to obtain the expected transmittance. Is that enough to represent all the sample? Again, it depends. So when Melanie says it's sufficient to obtain the expected transmittance, if there are people out there that don't use HORIBA's laser diffraction analyzers, we use something
called...
Shame on you. Yes, shame on you, absolutely. Freeloaders. No, I'm just kidding. We use something called laser transmittance as basically an optical concentration. It helps the user determine when they've added enough sample, when they've added not enough or too much. So Melanie's question is essentially, if only what seems like a tiny amount of sample gets into the expected transmittance range, is that enough to represent all the sample? That depends on a few factors. If the sample is colored or opaque, then you're going to be absorbing some amount of the light. So kind of classic example is if you are measuring powdered carbon black. Let's say the median size is maybe 500 nanometers once it's dispersed. Putting 0.1 grams of 500 nanometer carbon black in the analyzer almost certainly won't be enough to represent the sample, because so much of that sample will absorb the red and the blue light in the instrument that we use to generate the good scattering data. So let's say you have one very large particle in there. That one very large particle may be absorbing the light, so much of the light, as opposed to scattering the light. So you, in the case of colored samples or opaque samples, generally you want to add a little bit more. If it's a very wide distribution, 0.1 gram may not capture all of the different particle sizes in that wide distribution sample, in which case you would want to add a little bit more. It's an easy test to do. Try and add 5 times the amount of sample and see if all of a sudden now you're seeing larger particles than you saw before. That would be a good indicator that 0.1 grams is not enough to represent the entire sample.
And you just have to do the test, right? You have to do your subsampling and make sure that what you're splitting is representative of the whole. So you'd have to go through the procedure we discussed today and make sure that if you do reproducibility studies and you're meeting the expectations, then you stop worrying about it.
Mm-hmm. Sort of follow-up question to the wet or dry question earlier. If they want the sample to stay in the naturally agglomerated form, I would run it dry, and I would run it without any air pressure to de-agglomerate the particles. So just leave the air pressure off, run it dry. Generally, if you're going to run anything in a wet dispersion, as Mark said earlier, the surface tension gets lowered so much, or the interparticular forces get lowered so much that they kind of naturally disperse, even without any surfactant, even without any kind of mechanical energy being added. Let's see. Tom says that he admits not using HORIBA laser diffraction. He uses the HORIBA cam sizer. Well, so long as it's a HORIBA product, that's fine.
We're still best friends.
BFFs. All right. There's another question about refractive index of new material from, I hope I'm pronouncing this correctly, Tushara. Tushara, I'll send you a link to the refractive index webinars and other material we have on our website. That's probably a little bit better for you and for the rest of the audience. There's an awful lot that we could cover talking about refractive index, but very briefly, if you have a new material, a novel material, if it is truly novel, no one will know what the refractive index is, so you should send that to a contract lab if you don't have a refractometer or a microscope in your own lab to measure it. Or you could use a function in the 950 software called the Method Expert to try and approximate what the refractive index should be.
Yeah, and first just test to make sure it matters. You measure it once and then change refractive index. If you get the same answer, no matter what you put in, you stop worrying about it. If you get a very different answer, making different choices of refractive index, then you stop and do your homework. So just make certain first it matters.
Jay says that we mentioned earlier that zeta potential measurements of powders can be problematic. He would like us to discuss this further. So this is up your alley, Mark.
Zeta potential is generally thought of as a function of the surface chemistry of a dispersion. So zeta potential is the charge on the surface of particles, the easiest way to think of it. And so that implies they're in a suspension. And zeta potential is a measurement of the surface properties of the dispersion we're investigating. You could change the pH of the suspension. You might get different results. Maybe if you used a different liquid to disperse them, you'd get different results. So you need to disperse a powder in liquid before we start talking about zeta potential. You don't really talk about the charge on the surface of powder particles. You might have a static issue, and you might have to find out ways to remove static to do measurements. But zeta potential is only a measurement of particles in suspension, so that precludes measuring zeta potential of powders. So we only measure it of suspensions. And what I usually tell people in the lab or people out talking to customers, if a customer says we want to measure zeta potential of a powder, I say, well, disperse it the way you're going to use it, and then we do the zeta potential measurements for you. Because the dispersion is all important with the measurements we make. And so we usually just say, well, you disperse it, tell us how you're dispersing it, then we'll do the zeta potential measurements.
Thanks, Mark. I should say that I just typed into the chat box to everyone that you'll all receive a follow-up email from GoToWebinar in the next few hours with the link to download the slides from Mark's presentation. I apologize I wasn't able to get the presentation up onto our website ahead of the webinar, or I would have shared the link. And this is another opportunity for me to say, too, that our website is horiba.com/particle. That's www. Put that into the chat box as well. This webinar is recorded. It will be posted up on the website in the next few business days. And you'll be able to find it in the Download Center under the Webinars tab, under the Webinars area, I should say. And it'll be labeled something like Sampling for Particle Size Analysis, or the Importance of Sampling, something like that. It'll be in the Training section. And when you leave the webinar today, you'll be presented with an opportunity, a link to take a quick survey. Please do, if you have 4 minutes to spare, please do take the survey. We look at all of the responses. It helps give us some feedback as to how effective the presentation was, if it met your expectations. It'll give you the opportunity, if you think doing a guest webinar with us is something you'd like to do. It would be a way of showing your application to our audience, if that's something you'd be interested in. It's a way for you to let us know through the survey. And, you know, there's just a general comment section, so if you have anything you'd like to ask or anything you'd like to share, that would be a good opportunity as well. Let's see.
And I look forward to trying to get some information on that toughest question of what to do if we don't see the powder but we see them on the sieves. So, you might want to send me an email, Ian, to remind me to talk to some people about that, please.
Will do. So Pragna is asking, would you recommend using the refractive index of the maximum amount of one type of particles while measuring the particle size distribution of mixture of particles? An example would be a mixture containing 10% of A and 5% of B. Use the refractive index of 10% of A. Interesting question. I'm trying to avoid giving you the answer we've given for the other refractive index questions of just look at the webinar, but I will make a note to send you the links for that as well. What I would say is if the materials are different sizes, a lot of times what I like to do is, and you know the refractive index of both materials, calculate the distribution using the refractive index of one material, and if you know that material A is the smaller of the two, use the refractive index for A. Note, use the multimodal function in the 950 software to get D10, D50, D90, mean, all that information on material A's distribution. Then recalculate the result with the refractive index of material B. Again, use the multimodal report, get the D10, D50, D90 of now the more accurate material B peak, and use those two pieces of information to drive to your decision making. Or the the fast and dirty way of doing it is, if material A is more important to your process or your product quality, use the refractive index of material A. Whichever refractive index you use, if it's the refractive index of material A or the refractive index of material B, that will be the more accurate part of the distribution. An extreme example would be mixing PTFE Teflon with titanium dioxide. Let's say rutile titanium dioxide, where you have a very large refractive index and a material that has a very small refractive index, very close to water. That's an extreme example, but that would be an illustrative one, where if you use the refractive index of titanium dioxide to look at the entire distribution, no doubt the polymer component would be much more inaccurate than if you use the polymer refractive index.
I think this has generated an idea of an excellent webinar for you to give soon, Ian, on advanced software features in the LA950. I think that would probably be a good webinar.
Advanced software features. I like it.
Because that multimodal report's a really powerful tool, and you have to know how to use it, right, to get the best out of it.
writing a note. Melanie, so this will be the last question we address. Well, actually, there's two we can do real quickly. Damon's still here. Good. Do you know what level of reproducibility users try and achieve for soil particle size distributions? I imagine it might be greater than 1% with subsampling a 500-gram soil sample. That is, that's not something. Truthfully, it's not something you should ask the vendor, because we're going to give you a larger value than what some of the users do. What I can do, Damon, is I think you might have attended Dr. Andy Ward's Soils webinar last week. I can get you in contact with Andy if you'd like, and you can discuss it with him. He's much closer, obviously, to the application than I would be. I would be very hesitant to put words into our users' mouths. But generally, yes, soils are a more challenging application than many because the distribution is so wide and they constitute several different densities. So the reproducibility values go up. You know, trivial samples like latexes, those are so well behaved you could get great data, you know, falling asleep. Soil particle size distributions are a little bit more challenging, so we would expect the repeatability and reproducibility guidelines to expand as well. But an actual number is hard for me and probably not my place to say. Last question of the webinar comes from Melanie. Should it be possible just to lower the transmittance so I can put more sample and also by adding more water?
Careful with that. Multiple scattering concerns. When you dilute, you could be doing some problems there, but go for it.
Well, no, I think you've got it. Yeah, so there's two areas where, you know, if you're looking at materials coming out of a mine, it's probably the dispersion's not so critical. I think one of the things Mark was worried about is if you have a complex dispersion, let's say a chemical-mechanical polishing slurry. So you have very small ceramic particles that, you know, if the pH changes, let's say if you dilute by adding more water, that could shock the system and cause aggregation. So that's a concern. If the samples are sensitive to the environment around them, simply diluting with distilled water or deionized water can shock the system and cause problems. The other thing he was alluding to is the onset of multiple scattering. So if you have too many small particles, or really just too many particles, period, inside the measurement zone, what happens is the light strikes, the light from the laser or the blue LED, strikes one particle, deflects, which is what we want, but then hits another particle before it reaches the detector. And so every time the light, let's say the photon, hits a particle, it's changing the angle of scatter. And the way the instrument interprets these measurements is the wider the angle the light is scattered onto, the smaller the particle should have scattered it. So multiple scattering manifests itself as the distribution either shifting finer and finer or a new population of ultrafine particles always below 1 micron all of a sudden appearing. So that's the danger of simply adding more and more sample. Is you might start multiple scattering and you might think that you have finer material in the analyzer than you really do. All great method development questions though, and Melanie, I think I believe it was you, I believe you called me maybe 2 months ago, something like that, right before you purchased the LA950. I'll send you an email, as I've already promised, after the presentation, and maybe you and I should work a little bit more on method development. You have excellent questions, and they deserve a little bit more than a Q&A session at the end of a webinar. So, that said, that will be the last question today. If you have any more questions, feel free to email us. I'm putting in our general purpose email address, labinfo@horiba.com. My last name is Trevoranis and almost impossible to spell unless you know me personally, but I'll put it in there as well. You'll also be receiving an email from GoToWebinar that has my email address in there, so if you'd like to send anything directly to me, that's the easiest way. I also received the lab info email, so that's probably easier to remember and definitely easier to spell. So yeah, thank you everyone for attending the presentation today. Thank you, Mark, for giving the presentation. That was a very active Q&A session. Glad everyone was.
Yeah, enjoyed it.
Yeah, glad everyone was active and enjoying the presentation. So I hope you all have a great rest of the day, and if you're on the East Coast, I hope you're safe and dry and stay that way. Bye for now, everyone.
Okay. Au revoir. Bye for now.